Hello, welcome to Vedial Vagaparai. In this video, we are going to see meta-coupling of aromatic protons, a numerical based on GATE 2024 question. And this is an example of a long-range coupling. So let us see the question first. Consider the following proton NMR data of a compound. Chemical shift values are given and the compound is. So there are 4 compounds that are listed here and we are asked to find out the compound based on the NMR details that are given. So it's a very simple question, but at the same time, there are a lot of new things that we can learn from this particular question. So this question, we are going to see what is meta-coupling, what are the different types of coupling that can be noticed in an aromatic organic compound. So the most important coupling that we are going to see in this particular video is about long range coupling or proton-proton coupling involving 4 bonds. So the notation given here is 4J. So the normal proton-proton coupling is usually across 3 bonds and it is 3J coupling. So a long range coupling is a very weak coupling and we know it will have very small values. So but then for pi systems which have double bonds, we see that this coupling is quite prominent and they have values ranging from 1 hertz to even 7 hertz. So we see here in this particular case, in case of the allylic protons. So I am marking the allylic protons, and in these allylic protons, these two protons are actually 4 bond distance away. So 1, 2, 3, and 4. So in spite of being 4 bond distance away, that is they are on the alternate carbon, not on the carbon adjacent carbon, but on an alternate carbon. So such kind of protons can also couple and cause splitting of their NMR signals of each other. And this is called as a long range coupling. Similarly, we see here in the second example wherein the protons which are meta to each other are shown. These two protons again are across 4 bonds, 1, 2, 3, and 4 bonds. And so we see in an aromatic compound also there is a double bond, and because of this double bond you see the long range coupling here. Similarly, we see for propagylic and alene compounds also. So in all these cases, we see the protons which are 4 bond distance away have a characteristic coupling, and we can see them significantly pronounced in the NMR spectrum. So let us go to the next property. So let's take this example. So how we will see this spectrum. In this spectrum, it is pointed out that HA and HB are meta to each other. There can be a substituent in between. It is not that there shouldn't be any substituent. Even if there is a substituent in between the two protons, these two protons will couple each other. So when we say they couple each other, we know it follows the same n plus 1 rule. So HB is coupled by HA. So since there are no other protons, this HB signal will be a doublet, and similarly HA is coupled by HB, and so HA is also a doublet. But the J value or the splitting constant value for these two protons are so small because they are long range coupling. So this kind of coupling is seen only in case of aromatic protons which are meta to each other. And if you don't see this kind of splitting in an aromatic compound, then you can be very sure there is no meta proton in that particular compound. So we will see some more detail. Since we said meta, then there would be a question on what happens to the orthoprotons. Okay, orthoprotons we have already studied. They will couple each other. That's a normal coupling, J3 coupling. But then what is the coupling? If they are non-equivalent, what would be their coupling constant value? So we see here in case of orthoprotons, if they are non-equivalent, their values range from 6 to 10. So it's very huge. Whereas if they are meta, then it is pretty small and it is a J4 coupling. So in this particular example, we see here three different protons are pointed out, assuming X, Y, and Z are substituents, and we have proton at A, B, and C positions. So if there is a proton in the A position, it will be coupled by the proton in the B position. So A signal will be split into a doublet. That is what is pointed here. A signal is split into a doublet. And A signal is split into a doublet because of its normal coupling. And because it is normal coupling, the J value will be between 6 to 10. Here they have pointed out it is 8.585 hertz. Now, which is as expected because these two protons are orthoprotons. Now, let us look at this B proton. This B proton is coupled both by the A proton and the C proton. But then B is coupled by A by means of J3 coupling, whereas it is coupled to C by means of J4 coupling. So, the first it will be coupled with A to form a doublet, and the doublet will be split into a doublet. So what you will get will be a doublet of a doublet. It's not a quartet, it is a doublet of a doublet. So first a doublet with the higher J value. You see J value is more than 8, so it is around 9. So that is because of coupling with the orthoproton, and the second splitting of this doublet is due to the coupling with the C proton, which has a smaller J value, which is around 2. So that you see here that in case of B, there it looks like it is actually split into a doublet of a doublet and not a quartet. And then now coming to C, C is coupled to B. So we know this is again a long range coupling. If B is coupled to C, C would also be coupled to B. So this long range coupling would split the C proton into a doublet. So we see this is a doublet, and its value, because it's a long range coupling, is only small, pretty small, which is around 2. So in toto, what we must remember is, in case of aromatic protons, there is coupling between orthoprotons, metaprotons. Of course, there could be coupling between paraprotons, but the values are even more smaller, and it is negligible, and it will be unidentifiable in an NMR spectrum. But metaprotons are usually prominently noticed, and they give significant splitting of NMR signals, and so they can be usual or good indicators to arrive at the structure of an organic molecule or aromatic organic molecules. So let us go back to the question now. So now in this question, there are 4 different chemical shift values that are given. And now we will assign these values and try to identify which among these 4 options are correct. So let us take down the first value, which is 3.85, and it is a singlet, and it is due to 6 protons. And we know in all these molecules, no other situation will give you a 6 proton other than the OMe group, because it is a tri-substituted benzene ring, and so the aromatic compound has only 4 protons. It can be in any form, but it has only 4 protons, and the acid group has only 1 proton. So the additive value of these two methoxy groups only will add to 6 protons. So this 3.85 is due to the methoxy groups, and because it is a singlet, it is clear that both the methoxy groups are equivalent. So when we see the structures, observe the structures, we see that in structure 1, we have a methoxy group, and the next methoxy group being in the same environment, because both of them have an acid group to the as a neighbor on one side, and they have a similar structure on the other side. That is, it has protons, 2 protons and a proton here. So this is the structure wherein we see the methoxy groups are symmetrical. Similarly, let us see the next case. Again, here we have the methoxy group, and they are also equivalent, because we see their neighbors are all same. So there are surrounded by same neighbors. That is, in the alternate position, they have the acid group and a proton in between. So both of them are in same environment. So A and B are having methoxy groups which are in the same environment, in the sense this value could match up to any of these. And then coming to C and D. So in case of C and D, we see OME, or both the OMEs are in different environments. Uh, in C, this OME has acid as a neighbor, whereas this OME has OME and a proton as a neighbor. So C is ruled out. Similarly, in case of D, this OME is attached to carboxylic acid group. Ortho position has carboxylic acid, and another OME has carboxylic acid is a meta position. So in both C and D structures, the methoxy groups are different, and so the two structures are ruled out. They are not the answers. We need not search for the answer in these two structures. So next, what we have to see is about the 13 BRS means it's a broad band, broad singlet. BRS means broad singlet. So 13 broad singlet is due in all these structures. We have the carboxylic acid group. So all of them would give a broad singlet at around 13, which is due to the carboxylic acid group. So that is also not going to give us a option to find the correct answer. So next, what we will see is the two sets of protons, which are the aromatic protons. So in these two cases, A and B, we see there are three aromatic protons. Both of them have three aromatic protons. And from our splitting values, assuming let us say we will number the protons as H1, H2, and H3. H1, H2, and H3. Similarly, here also we will number the proton as H1, H2, and H3, or we will number them as HA, HB, and HC. So let us take option A. In case of option A, we know that H1 and H2 are similar, and H3 are similar because they have the same environment. H1 has a OME as a neighbor and H2 as its neighbor on this side. H3 also has OME and H2. So H1 and H3 are equivalent. So we will give them the same numbering. So they are similar. Okay, they are similar. They will give the same signal. So there will be two sets of signals, one signal due to H1, another signal due to H2. So there are two sets that are given here for the aromatic proton. And splitting also, when we say H2 is split by H1, so it will be a triplet. Two H1s are there, so H2 signal will be a triplet. Similarly, H2 signal 2 plus 1, H2 will be a triplet. Similarly, H1's neighbor is H2, so this will also be a doublet. So this H2 will be split by H1. Likewise, H1 will be split by H2. So again, here H1 signal will be a doublet, H2 signal will be a triplet because there are two protons. Okay. So here we see two proton, one proton is given, and H2 is shown as a doublet. Okay. Two protons, this is two protons, so they are doublets, and this is one proton, and so it is split into a triplet. So this is matching for A. So similarly, let us see for B. B again, we have studied that there will be coupling, there will be meta coupling. So because there will be meta coupling, there are three meta protons, though there is no ortho proton. So this is actually J3 coupling. But then there, because these three protons are all different, what we will think is there is no coupling, and so the signal will be a singlet. But then they are not singlets. There three different singlets will be coming. No, it is not like that. So there is meta coupling here. So there is J4 coupling possible. So if J4 coupling is possible or meta coupling is possible, Hc signal will be split by Ha. So and B, Ha and B again are same. So we will denote them as Ha, and Hc will be a separate one. So we see these two protons that are ortho to the two protons that are ortho to the carboxylic groups are similar, and one proton in between the methoxy group is different. So because this is surrounded by methoxy group, whereas these two are surrounded by hydrogen. So sorry, these two groups mask A, and these two also is A. So these two are same, this is different. So you have two protons which are similar and one proton which is same. So but then splitting, we would think that they will give, they may not give a splitting because they don't have n plus 1. But then here J4 coupling is possible, and because J4 coupling is possible, B signal will be split by the two Ha protons into a triplet. Okay, so the Hb signal, which is due to one proton, will be split into a triplet. Similarly, Ha signal, which is due to two protons, will be split into a doublet. So both A and B gives the same set of values, that is a doublet and a triplet due to single proton and a double proton. But now the only decider in this case is the J value, So because A is due to J3 coupling, the J value must be around 7 hertz, that is 2 to 10 hertz. Whereas in because this is J4 coupling in case of B, the value is around 2 hertz. Okay, it must be between 0 to 4 hertz. So, but then the J value that is given here in this case, so we must remember that the J value that is given here in this case is only 2.2. So though we see there is only J3 coupling here and there is J4 coupling here, but the spectrum data shows that the J value is significantly prominent, and we know now that it is due to meta coupling and not due to ortho coupling. So because it is not that, this particular option A is not the answer for this particular question. The correct answer is B. So B is the correct answer because this one satisfies the given set of data, especially the J value, wherein the J value is small when compared to the expected J value for a orthocoupling. I hope you understood. Thank you.